objects. Okay. All right. It's the first talk, so we got to get these technical difficulties out of the way. Okay, so the objects that we're studying are Hénon-like renormalization, which are 2D analogs of 1D unimodel maps, which, if you recall, is there a way to get rid of the bar at the top? Click OK. Okay. So 1D unimodel maps, it's a map on an interval to itself, and its defining characteristic is that it has a unique critical point, right? And throughout this talk, critical points are always assumed to be quadratic for simplicity. So the way it maps the interval, it takes the interval, it folds it once at the critical point. Okay, so that's how it acts on the interval. And a Hénon-like map is a 2D diffeomorphism defined on a rectangle. And the definition's here. So in coordinates, it's of this form, where the second coordinate is just x. And the first coordinate, once you fix any y value, is a 1D unimodel. Okay, so this is a Hénon-like map. And it's kind of obvious, implicitly assumed in this definition, that the first coordinate, the x coordinate, is the one that should play the more dominant role, right? And we make this implicit assumption explicit by considering what I'll call thin maps. So we say that a Hénon-like map is beta thin for some beta less than 1 if the dependence on the second coordinate on y is less than beta. So let's try to visualize how a Hénon-like map transforms the space. So it acts on a rectangle, like I said, and I like to think of it as doing the following. So first, it'll compress the rectangle vertically into a thin horizontal strip, and then it will bend that strip into a sideways U shape, like this. Okay, so this is the action of applying the Hénon map once, and for the dynamics, we of course want to iterate this procedure. And the reason why I call this thin, because the thinness refers to the thinness of the image, right? So as beta goes to 0, the image will collapse into a curve, which actually coincides with the graph of a 1D unimodel map. It'll be a parabola. Okay. It's useful to have some consistent way of assigning a 1D approximation to your Hénon-like map. So we define a 1D profile of a Hénon-like map, capital F, to be, you just take the first coordinate, the little f, and just plug in some fixed y value, right? Which for simplicity, we'll just take to be 0. Okay, so just plug in 0 into the first coordinate, you get a 1D unimodel map, and that is called the 1D profile of your Hénon-like map. And if your Hénon-like map is thin, then at least for the first few iterates, the Hénon-like map will be approximately, well, it'll act like its 1D profile. Of course, over long term, the second coordinate starts to play a huge role in how the dynamic goes. Okay. So this is the object that we're interested in. Any questions up to this point? So far, I think it's pretty okay. You might ask why we care about the Hénon-like maps. So let me justify it in this way. So the reason we care about unimodel maps in 1D is that it's the simplest system, 1D system, that features a critical point, right? So it's kind of the model to look at if you want to understand the dynamics of a critical point. Well, a Hénon-like map is the simplest 2D system that tries to force the 2D analog of a critical point, which is, well, it turns out to be a tangency between a stable manifold and a center unstable manifold. Okay? So this is kind of the reason why we want to study Hénon-like maps. But I'll maybe talk more on that later on. So the model examples of Hénon-like maps are given by the Hénon maps, which are expressed in this form, right? So it's a 2-parameter family. It has 2 parameters, A and B. So you can visualize it on a plane, a real 2-dimensional plane. And I like to put the A parameter on the horizontal axis and B parameter on the vertical axis. A quick computation will show you that a Hénon map has constant Jacobian, which is exactly equal to the second parameter B, right? So as you travel down on this space of Hénon maps, you start from area expanding Hénon maps when B is bigger than 1 to area preserving or conservative Hénon maps when B is equal to 1. And then between B equal to 1 and B equal to 0, you have the area contracting or dissipative, or, to use the previous term, thin Hénon maps. And then when you go down to b equal to 0, then your Hénon map degenerates, right? And notice that on this line, on the line b equal to 0, if you look at the formula, this term disappears, and we can actually identify that line with just the standard one-dimensional real quadratic family, right? So the dynamics on here is very well understood after nearly 4 decades of work by many, many mathematicians. And at the heart of this development was renormalization theory. So I think it's kind of plausible that renormalization, its extension of it, will play an important role in the understanding of the 2D Hénon maps, right? Which is like a 2D extension of the quadratic family. Okay. So this is kind of our goal, right? To develop this extension of renormalization theory. And let me start by telling you what the main conjecture we want to work towards is. Okay, so this is the main conjecture when it comes to the topic of renormalization of dissipative Hénon maps. So let's first look at the infinitely renormalizable maps on this line, which are just infinitely renormalizable quadratic polynomials. And like I said, that is understood extremely well, right? So we know where the infinitely renormalizable quadratic maps are. We know in which order they appear. We know their topological and geometric properties and so on. So those are very well understood. So for example, I plotted a few of them. So the very first infinitely renormalizable quadratic polynomial that you encounter is the famous Feigenbaum quadratic polynomial, where the combinatorics is period doubling. And then there's also, somewhere off to the left, there's period tripling. And then somewhere in the middle, it's period 3, and then period doubling, and so on, right? So I just plotted a few. And the conjecture that we want to work towards is the following, that if you take any one of these infinitely renormalizable quadratic polynomial, then there grows out a real analytic curve starting at this infinitely renormalizable quadratic polynomial that extends all the way up to Jacobian equal to 1. So this is the main conjecture, right? And if you take one of these curves, then on that curve, every Hénon map is infinitely renormalizable. And under renormalization, again, if you're not familiar with renormalization, just think of it as a process in which you zoom in to reveal the small scale dynamics, okay? So if you are on one of these curves, you can zoom in infinitely many times. And as you zoom in, the picture that you see will converge to the same thing that you converge to at the base point. Okay, so on this curve, the renormalization convergence, it converges to the same limit. Okay, so this is the main conjecture that we want to work towards. And in case you're not interested in renormalization, there's an independent reason why you should care about these curves, and it has to do with the emergence of chaos in this family. Okay, so if you look at this family of Hénon maps and you look towards the right, way off to the right, then the dynamics is just, everything marches off to infinity. Okay, so the entropy is 0 when you go far enough to the right. If you go far enough to the left, then the map you have is just a classic horseshoe, Smale's horseshoe. So you have the maximal entropy when you go far enough to the left, right? And entropy varies continuously in this family. So that means that there has to be at least one separatrix that separates the region of 0 entropy with region of positive entropy, right? If there's more than one such region, there will be several separatrixes, but there's at least one, yeah? So the conjecture is that if you take the union of all these curves and you take the complement, then the leftmost component will be the region with 0 entropy, okay? And then everything else has positive entropy. So that means that the separatrix between the 0 entropy and the positive entropy, that is what we call the boundary of chaos. It will be a piecewise real analytic curve that extends from b equal to 0 all the way up to b equal to 1. Okay? And if this conjecture is true, then actually it has an interesting consequence that basically the transition to positive chaos, the only way to generate positive chaos in the 2D family, it's the same mechanism as in 1D, which is that it can only happen through a series of period doubling bifurcations. Okay? Because that's exactly what happens in 1D. So in 1D, everything to the right of the first infinitely renormalizable quadratic polynomial has 0 entropy. And then at the Feigenbaum, that's when the entropy starts. Okay? So this is the kind of the independent conjecture, why you would be interested. So this conjecture is based on some numerical simulations that dates way back to the 80s. And I think the conjecture or something similar to it was first proposed by Genboto Trese a long time, a surprisingly long time. I was kind of surprised that it had been standing for so long. And oh, I haven't mentioned my co-authors yet. The goal of my co-authors and I, so my co-authors are Sylvain Crovisier, Misha Lyubich, and Enrique Pujals, is to try and take steps towards proving this conjecture, and I think we made some meaningful progress towards it. But at this point, I should mention that the conjecture has been verified for what we call perturbative Hénon maps. So a Hénon map is perturbative if the Jacobian is really, really small. So it's just a small perturbation of a quadratic polynomial, the dynamics of a quadratic polynomial. In that case, you can actually verify that, yes, there will be, if you start from any infinitely renormalizable quadratic polynomial, small perturbation of it will give you infinitely renormalizable Hénon maps so that the convergence is the same. Yeah, and this can be proved using basically using the strength of what we know in 1D. Because in 1D, you have this renormalization, which turns out to be an analytic operator in the space of dynamical system. And this operator happens to be hyperbolic. So it's robust under perturbations. So just using a perturbation method, you can make sure that the nice renormalization convergence you have in 1D extends at least slightly to 2D, right? But what we want in order to prove this conjecture is to actually go all the way, very far away from the 1D system. In order to do that, you need to develop a non-perturbative theory of 2D renormalization. And this is exactly what I'm going to be talking about today. All right, so that's the motivation. Any questions? Okay. Yes. Okay. Well, I was a little bit sloppy, maybe, or I didn't mention that the conjecture is only for infinitely renormalizable quadratic polynomials of bounded type. So the relative period should be uniformly bounded. And then there should be a curve which extends out all the way up to. Was that your question, or yeah? No, I mean, we don't know counter examples, but I think, yeah, I think it should be very possible to construct an unbounded type infinitely renormalizable quadratic polynomial for which there's no way to extend it. I think it should be possible. As soon as the relative periods start to go up, some bad things start to happen. Okay. All right. So since I'm going to assume that you're sufficiently motivated, I'm going to start with the actual topic of the talk, which is renormalization of these Hénon maps. Yeah. So renormalization in 2D is more intricate than renormalization in 1D. So what I'm going to do is I'm going to start with the most basic notion of renormalization, and then I'm going to have to refine it 2 more times. Okay. So the most basic notion of renormalization is purely topological. So it says that a Hénon-like map is topologically renormalizable if you can find a subdomain inside your phase space, which under the dynamics goes around a couple times, and then after you apply some period number of iterations, the image will go compactly inside where it came from. Okay, so this domain is referred to as a periodic domain. So if the period is R, it's an R periodic domain. And once you have such a domain, then we say that this map is topologically renormalizable. Yeah? So let me just kind of comment back to the informal definition that we had. So when you have this renormalizability, you have a kind of self-similarity, right? This is purely topological, so you have a topological self-similarity, right? In the following sense, if you look at the original Hénon-like map, topologically speaking, all it is just a map defined on a rectangle topologically is just a disk, right? So it's a map defined on a topological disk, and it maps it compactly into itself, right? That's all it does. That's all the original map does. And if you have this periodic domain, then you can see that if you take the return map to this domain, then again, you get a topological map defined on a topological disk that takes the disk, maps it compactly inside itself. Okay, so we have this self-similarity acting on a smaller scale, on this smaller subdomain. Okay, so this is a small scale self-similarity. But of course, this isn't good enough because we don't want to just forget about the Hénon-like structure. Right? That's going to be essential for us. So we refine topological renormalizability to Hénon-like renormalizability. So we say that a topological renormalizable Hénon-like map is Hénon-like renormalizable if on this periodic domain, you have a smooth change of coordinates, right? That defines for you vertical directions and horizontal directions. And in this new coordinates, the return map will be again Hénon. Okay? So this is a Hénon-like renormalizable Hénon-like. Okay. Yes. And the only technical condition that we put, kind of more so for convenience than anything else, is that it will preserve the horizontal directions. Okay, so the horizontal directions will remain fixed under renormalization, but other than that, no other conditions on this. And if you are Hénon-like renormalizable, then we call the pair, the return map, and this change of coordinates, which we call a straightening chart. That pair is referred to as a Hénon-like return. And then we can define renormalization, this action of zooming in the following way. You take the return map, you put it in the right coordinates so that it's Hénon-like, and then you rescale so that the width becomes standard size. Right? So this way you zoom in and you see what's happening at the smaller scale. Okay, so this is Hénon-like renormalization. Let me point out an important difference between 1D renormalization and 2D renormalization. Because in 1D, if you take a reasonable unimodal map, so for example, if you take a quadratic polynomial, then actually there's no need to define two notions of renormalization, because if you have topological renormalization, it automatically implies unimodal renormalization, right? So if you have a unimodal map acting on an interval and you have a periodic subdomain, then actually you can show, for quadratic polynomials at least, that it has to pass through the critical point exactly once, okay, this periodic subdomain. So that means that if you look at the return map to the subdomain, then it will fold exactly once when it passes the critical point. So when it comes back, it will again be automatically unimodal. But in 2D, that's not the case. So even if you take the nicest Hénon-like map, so if you take the Hénon map and you find a region which maps back into itself after some finitely many period, there's no guarantee that the return map will look anything like a reasonable Hénon-like map. Okay, there's no guarantee that on this quadrilateral, you'll have this kind of vertical contraction and bending into a U shape. And I think the reason for this difference in circumstance has to do with the fact that for 2D diffeomorphisms, there's no single pinpoint location where the critical point does its thing, right? Where the critical point is. But it turns out that such systems do have a meaningful natural notion of a critical orbit. But in order to try and locate where it is, in order to try and get a hands on how it influences the dynamics, we needed to incorporate some elements from smooth dynamics, right? In particular, Pesin theory, or at least our reformulation of Pesin theory. Okay? But in order to access this methods from smooth dynamics, we needed this one last final refinement of renormalizability, which we call regular renormalizability. Okay, so the actual definition is slightly technical. It's not too bad, but I didn't want to put any kind of technical details here if I could avoid it. So let me define it for you extremely loosely. Okay, so let's say that you have this Hénon-like renormalization. We say that it is regular if it satisfies the following two properties. The first property is that for any point that you take in this periodic domain, if you look along the vertical direction, again, given by your straightening chart, then along this vertical direction, it should act like the stable direction under forward iteration up to the return time. Okay? So this is a key important part of this assumption, because there's no way that you're going to get every point to act along the vertical direction like a stable direction for all time, because if that was true, actually you can prove that this thing won't be further renormalizable. Okay, so if it's infinitely renormalizable, there's no way to get stable like behavior throughout the region for all times, but you want to assume it at least up to the return time. Okay? So along the vertical direction, it acts like a stable direction, which more or less means that if you look at the growth rate under the dynamics, you should see something like exponential contraction up to some fixed error. So this is the first assumption. The second assumption is a little bit more delicate, maybe, a little bit harder to understand. But it's not so bad. So the second assumption is that if you take the horizontal direction and you push it forward to the return time, then the resulting directions, the image of the horizontal direction, should act like a center direction up to well, when you iterate backwards up to the return time. Okay, so if you look at the directions that line up with the image of the horizontal direction, and then you start to iterate backwards, then what you see along those directions should be something like, well, neither exponential expansion or contraction. Okay, it should be something neutral, right? That's what center direction means. So these are the two assumptions, and once you have these two assumptions, then we can prove our main theorems, which are, any questions? So this is the definition of renormalization that we need in order to prove our theorems. Okay, if not, then our theorems are about if you take a Hénon-like map and you renormalize it many times, what is the asymptotic behavior of renormalization? So what happens when you take a Hénon-like map and you zoom in on the small scale dynamics? So we need a setup, right? So we assume we have a Hénon-like map, which is many times renormalizable. So we're going to have a nested sequence of periodic domains, which I call B1, B2, and so on. And on this periodic domains, well, there's returns after the periods. So the periods I denote R1, R2, and so on. And on each of these domains, there's a straightening chart, which turns the return map into a genuine Hénon-like, right? And we call these straightening charts psi1, psi2, and et cetera. Then the renormalizations, so we get a sequence of renormalizations because we have infinitely small, arbitrarily small periodic domains where we have the return maps. So the renormalizations is denoted by this fancy R to the n of capital F. So that denotes taking the nth return map, straightening it by the straightening chart, and then rescaling to be of unit size. So we get the sequence of Hénon-like maps, and we want to know what happens to this sequence of Hénon-like maps. And I should mention at this point, it's something that I kind of alluded to, but I'll define it now. We say that this Hénon-like map is of bounded type. And if you give me a number, then it's that number bounded type. So for example, this B could be, I don't know, 4, right? Then it's 4 bounded type. If the relative periods, as you go from one renormalization scale to another, is uniformly bounded by 4. Okay? So this is the setup for our main theorems. So the first thing that we establish is, well, yes. Okay. So the rescaling is affine. So after you do the straightening chart, you don't do anything more nonlinear. Okay. After that, you just, you expand the same way in both directions, and then you do some translation to put the origin at some place. So the straightening chart is the more complicated way. But of course, part of our theory is to say that actually it's not so complicated. At least asymptotically, it's not so. Yes. Okay, so the first thing that we have to establish is what is called a priori bounds, right? So this is kind of a standard thing that you need to have a functioning renormalization theory. And loosely speaking, a priori bounds means that you have some uniform control on the geometry, on the small scale geometry that holds at all renormalization depths, right? Another way to put it is if you have a priori bounds, that means that when you zoom in, what you see doesn't get uglier and uglier. Okay? So it remains something reasonable when you zoom in. So what does it specifically mean in our context? Well, it's just like in 1D, we need to be able to control distortion. Okay? So I don't know if many people here are familiar with what distortion is for 1D systems, but basically it measures how nonlinear your map is, right? So let me define it. But we need the definition for slight generalization of that. So we need it for a map acting on a curve in 2D space rather than just on an interval in 1D space. So let's say that you have some curve in a 2D space and you have some diffeomorphism that acts on it, that we measure its distortion in the following way. So first you parameterize the curve, let's say arc length parameterization. And then in this parameterization, your diffeomorphism, you just get a 1D map going from an interval to another interval, right? And then the distortion of this map is equal to the distortion of this 1D map in the 1D sense. And that distortion is just the quotient, the maximal quotient of the derivatives along this interval, right? So if your map is linear, so the derivative is same everywhere, then the nonlinearity or the distortion will be just 1, right? But if it's nonlinear, and if it's highly nonlinear, so let's say that's in some places derivatives huge, some places derivatives small, then the distortion will be correspondingly big. Okay, so this is a measure of nonlinearity. And upright bounds for us means that we have the following uniform bound on the distortion. So if you have your renormalizable map, right? So you can go down to any scale, let's say scale n. Then what you can do is you can take your periodic domain, take a horizontal cross section, let's call that gamma n. And if you were to start iterating your map on this curve all the way up to the return time, all the way up to the period, then the distortion that is felt along this curve should be uniformly bounded, independent of n. So this is upright bounds in our context. Okay, so this will give you the control that you need in order to get the consequences that we're after, which I'll list right after this slide. Okay, so this is upright bounds. And typically, for when you're trying to develop renormalization theory, upright bounds is kind of the hardest ingredient to achieve, and the same is true here. This is the most technical part that we needed for our theory. Questions? No? Yes? Yeah, that's right. Yes. Same. Yeah, more or less. Yeah, more or less. Yes. Okay. All right. So what are the consequences of? So once you have upright bounds, so you have some kind of nice uniform control on the geometry. Here are the main consequences. The first one is renormalization convergence. Okay. So let's say that you have infinite regular Hénon-like renormalizability. Right. So you have this kind of nice folding of smaller and smaller rectangles into U shapes. Then you see the following asymptotic behavior. So first, let's talk about what the periodic domains look like. So once you go sufficiently deep enough, so the first thing that we can say is that the height of these periodic domains will stabilize. Okay, so if you have some periodic domain, you can actually extend the height to be of some uniform size. Okay, and the widths will actually shrink exponentially. So as you go deeper and deeper, you get these long rectangles of width, which is exponentially small, right? So in the limit, it will converge to some curve, which under the regularity assumption acts like a stable curve for all time. So therefore, it has to be the stable curve. Okay, so this is what the domains converge to. And if you look at the images, what you will see is a nested sequence of thinner and thinner parabolic strips. So in the limit, it will converge to a curve, a parabolic curve, which acts like a center manifold for all backward time. So therefore, it has to be a center manifold, right? And the fact that the image is contained in the domain, it forces this center manifold to intersect the stable manifold at a single point. And you can also see by the fact that you have a parabola and something vertical, that this at this intersection, these two curves will form a quadratic tangency, right? So this very special point where you have this tangency, we call the critical value for your system. Okay, so this is the 2D analog of the critical value for 1D unimodel. So this is what the domains and the images look like. Let's see what's happening with the maps. So first of all, the straightening charts, this non-linear change of coordinates that you apply to your return map. So if that just goes out of control, then you can't really say anything meaningful about what's happening with the normalization, right? But fortunately, it turns out that these sequence of straightening charts, it just converges extremely fast to some fixed smooth map, some fixed smooth diffeomorphism, which I think you can just take more or less anything which will straighten out this stable manifold to a genuine vertical manifold. So you take any kind of smooth map that does that, and it will, the sequence of straightening charts will converge to that diffeomorphism. Okay, so nothing dramatic happens with the straightening charts. In fact, it converges extremely fast to some fixed smooth map. And then also, if you look at the sequence of Hénon-like returns, they will be thinner and thinner. The thinness will go to zero super exponentially fast also. So the sequence of Hénon-like renormalizations, it converges to a one-dimensional system extremely fast. Okay, so then now what can you say about the shapes of these Hénon-like maps? Well, if you look at the 1D profiles, since it's going to 1D system super exponentially fast, you just have to worry about what's happening for its 1D cross-section, and its 1D cross-sections will converge, have the same kind of renormalization convergence behavior as just renormalization of 1D unimodulus. Okay, so to summarize, the straightening charts, they just converge to some fixed smooth map. The Hénon-like returns go to one-dimensional system super fast, and along the one-dimensional system, the same thing that you get for 1D renormalization happens in 2D. So this is renormalization convergence result. Questions about that? So if you have infinite regular Hénon-like renormalizability, you have this kind of convergence that we would want. Okay? But there's an issue here, which is, well, how difficult is it to guarantee this infinite regular Hénon-like renormalizability, right? So this is what I would like to address. Did you have a question, Artem? Yes. Yeah, so, and Andre Di Cavello, yes, so in the perturbative case, you can use robustness of 1D renormalizability to guarantee that you have this kind of picture for all infinite depths. Right, but the key point here is that we don't rely on this 1D robustness. Yes, yeah, well, I mean, yeah, so this is for, well, we'll discuss, yeah, you'll see. Okay, so so now the issue is, how do we guarantee this condition that we need in order to get the nice convergence result that we want, this infinite regular Hénon-like renormalizability. So this is addressed in the following two theorems. So the first theorem has to do with the regularity and the Hénon-likeness. Okay, so like I said, if you have a topological renormalizability of a Hénon-like map, there's no guarantee that what you'll see at the end will be something Hénon-like as well. Yeah. But what is true, what turns out to be true, is that if you can guarantee regularity for your Hénon-like returns up to some sufficiently deep depth, then all further topological renormalizations will automatically be regular and Hénon-like. Okay, so as long as you can go into sufficiently deep depth with regularity, all future returns will be guaranteed to squeeze and then bend into a U-shape. Okay, so this is what this theorem says. So it says that, okay, so let's say that you have this Hénon-like map, and let's say you can go down to some sufficiently deep depth, capital N, and this capital N, this is an important point, the capital N can be explicitly determined. It depends on just the C2 norm of your map, the Jacobian of your map, and the bound on the relative periods. Okay, so you can determine this capital N, how far you have to go in, and if you have regularity all the way up to that depth, then any returns, further returns that you have, starting from this depth, will be guaranteed to be Hénon-like with uniform regularity. Okay? So this is the kind of robustness that robustness of the regularity and the Hénon-like condition that we need in order to get the convergence that we want. Okay, good. So what's nice about this is that, well, it essentially turns checking for renormalization convergence into a finite condition as long as you have infinite topological renormalizability, right? But that in itself is a priori an infinite condition, but actually the next theorem says that you can get it in finite time as well. So this is what I call realizability. So it states the following. So let's take not just one Hénon-like map, but a one parameter family of Hénon-like maps. So let's say it depends C1 smoothly on this parameter A. Then the following is true. So let's say that all these maps are n times renormalizable, where the capital N was given in the previous slide. Okay, so all of these are sufficiently, are regularly Hénon-like renormalizable up to some sufficient depth, capital N. And moreover, in this depth, if you take the 1D cross-section, if you take the 1D profile, then you get a full family. Okay, so what that means is basically you have this kind of picture. So for each map in this family, you can zoom in up to n times in a regular way. And if you look at the nth renormalization scale, then by varying the parameter, you can get the picture to do this. So you can get, by varying the parameter, you can get it to look like this. Okay, so this is the fullness of the family at the nth scale. So if you have that, what you can guarantee is that for any combinatorial type, bounded type, there's a parameter in this family which is infinitely renormalizable with this combinatorial. Okay. So that and the previous slide guarantees that actually, yes. So infinite renormalization convergence can be checked in finite. So let's actually apply it to our Hénon maps to see how it works. So we have the Hénon family like before. And what we're going to do in order to get our one parameter family is we're going to fix the Jacobian. Right? So then you have this one parameter family of Hénon maps, and we're going to try and find a Hénon map which is infinitely normalizable and it converges to the 1D. Okay? So this is how it works. So I told you with the robustness theorem, once you give me the map, the C2 norm of the map, and you give me the bound on the relative periods, and you give me the Jacobian, then I can determine the depth that you need to go into, right? In order to propagate further regular Hénon-like renormalizability. Okay? The relation is explicitly given here. If you don't care, don't worry about it, right? But if you do care, let me just tell you that this capital D is just some independent constant. It doesn't depend on anything. And this capital K just depends on the C2 norm and the bound on the relative periods. Okay, this capital K is actually just the uniform bound on the distortion that you got from our previous. Okay, then you can determine capital N by choosing it big enough so that this thing is less than. Okay, so this is the relationship between all those things that I mentioned with this capital N. Okay, so let's try to apply it to our Hénon-like family in order to get this kind of non-perturbative convergence. So first thing that you can do is you can set, in this equation, you can set n to be equal to 0, right? So if n is equal to 0, then this Rn, which is the period at the nth level, is going to be 1, right? So you just want to solve for k beta to the epsilon is less than. Okay, so that will determine some beta small enough so that this will be true, right? So you look at the one parameter family of Hénon maps at that height beta, right? And if you look at the 1D cross section of this family, this is going to be full because it's just the quadratic family, right? So n being equal to 0 means that you don't have to renormalize in order to check the condition that you need, sufficient condition that you need for robustness, right? So you don't have to worry about it. You just take the 1D profile of the original family, which is just the quadratic family, and that's of course full, right? That's work of Milner and Thurston from way back, right? So you know that for any bounded type combinatorics, there will be an infinitely renormalizable map, which will converge, have the same convergence as in mind. Okay? So this is the first kind of application that you can have. And if you want to set your height higher than this B, then you can achieve this by letting the number of times you renormalize go up. Okay, so let's say you set some height higher, closer towards 1, then you can solve for n using this relation. And if you can do the following, then you can guarantee that you can find an infinitely renormalizable Hénon map at that height. So what you need to do is you need to find some interval at that height so that all the maps on this interval are capital N times renormalizable, and you have fullness when you move across this interval. Okay, then you know that there will be a parameter there which is infinitely normalizable, and it'll converge all the way. It will converge, have the same convergence as the 1D. So this is the application. Okay, so let me check how much time I have. What do you think? How much? 10 minutes? Okay, so I won't need 10 minutes. I'll just need 5 minutes. Okay, so the last result that I want to talk about is, yes. Yes, okay, so Xavier pointed out that, so we don't know that we have a curve, I guess. I mean, I would imagine that it's not so hard to go from what I said so far to getting a curve. But I guess technically speaking, from what I have, all you know is that there will be at least one point here which does converge to the same. Yeah. But yeah, I should also mention, I guess, maybe that checking for this condition probably requires some kind of numeric assistance, computer assistance. Yeah. But I think if the height is not so bad, so the closer you get to 1, the larger capital N needs to be in order to satisfy this condition, right? So if the height is not so bad, I'm kind of hoping for, maybe if beta is 0.1, for example, then the number of times you have to renormalize will be something reasonable so that you can actually check it on the computer. Right? Then you'll be able to say it. The curve will actually go up to that height, assuming that you verify it at the intermediate stages. Yeah. Yeah. Numerical evidence. So I mean, it's a question of numerical evidence for what? So I mean, numerical evidence states that the conjecture that I stated, that these curves go all the way up to 1, right? I mean, yeah, so that exists. But numerical evidence that we can check these conditions for height 0.1. I mean, that's yet to be seen, right? It's something I don't know. Okay, good. All right. So what do we have so far? We have the infinite renormalizability and we have this kind of convergence. And renormalization convergence is really nice because it means that when you zoom in at the critical value, what you see will converge to some universal limit exponentially fast, right? So the geometry around the point where you're zooming in, which is the critical value, is very, very well understood as a result of our renormalization convergence. But you can direct that question to more global, right? So you can now ask, what can you say about the global geometry of your map if your map is infinitely regularly Hénon-like renormalized? Yeah? So in order to kind of frame what I want to state, let me go back to the 1D case because it's always simpler, right? So the kind of question that I want to answer is the following. So let's say for 1D, you take a unimodel, 1D unimodel map, and let's say that it's infinitely renormalized. So it has this infinite nest of periodic subintervals, so that when you take the return, you get this kind of unimodel map. Then what you can do is instead of just looking at the piece containing the critical value and zooming in there, what you can do is you can take the full orbit, the full cycle of these intervals and take their nested intersection, right? Then you get a Cantor set, which is called the renormalization limit set. And if you're interested in the global geometry of your map, you want to understand the geometry of this limit set. Right? And what you know is by renormalization convergence, if you zoom in at the critical value, the geometry that you see will converge to some universal geometry exponentially fast. And now you can ask the same question for other points on this limit set. Right? So what happens to the small scale geometry elsewhere on this Cantor set? Is it also, do you also see some kind of universality, some kind of rigidity? Okay? And the answer is yes. So this is a result from McMullen in the quadratic-like case and DeMello Pinto in the general smooth case, is that you have actual rigidity of allowable small scale geometry for infinitely normalizable maps. Okay? So formally stated, it's like this. So if you have two maps which are infinitely normalizable and you have a topological conjugacy between the two normalization limit sets, then this conjugacy is actually forced to be C1 plus alpha smooth. So what does this have anything to do with the small scale geometry? Well, if you have a C1 plus alpha smooth map conjugacy between two renormalization limit sets, what that means is if you zoom in, this conjugacy looks more or less like a linear map, right? Because the derivative is constant when you zoom in, right? So when you go from one renormalization limit set to another, all you're doing is just a linear rescaling. So the relative distances between points in this Cantor set should be the same no matter which map you started. So the small scale geometry of infinitely normalizable map, it is rigid. You don't have, there's only one allowable geometry that you can have for this Cantor set. So this is the situation in 1D. What you can do now is you can take a 2D map. You can ask the same question. If you take the full cycles of renormalization domains and you take their intersections, so you get some kind of Cantor-like set, which is called the renormalization limit set of your 2D map. And then you can ask, well, is there some kind of rigidity, small scale rigidity for the small scale geometry of this Cantor set? And I can tell you that this question in the 2D setting is literally twice as hard as the question in 1D, right? And I can justify that because in 2D, when you talk about rigidity of small scale geometry, you not only have to worry about the relative distances between points, but you also have to worry about the direction of points. Right? Because the direction is also being transformed under your map. So let me try to illustrate what this means. So this was taken from the PhD thesis of Salma, who generously let me present it to you. So what he did was he took infinite renormalizable, or at least many times renormalizable Hénon maps of period doubling type. And he plotted the center direction field on the renormalization limit set. Okay? If you're not comfortable with Oscillatet's decomposition theorem, then just think of it as you have infinite renormalizable Hénon map. So just take 2 points that are very close nearby, take a line through these 2 points, and then propagate this line by the dynamics, this tangent line by the dynamics. Okay, and the result you plot on the. Okay, so this is what I'm showing you. So Salma, he took this Hénon map going from Jacobian equal to 0 all the way up to, well, something very close to 1. I think it's 0.95. And he plotted how these directions transform under the dynamics. Okay, so you start with when the Jacobian is equal to 0. So this is a degenerate case, right? So this Hénon map is basically 1D infinitely renormalizable quadratic polynomial. The only difference is that for 1D quadratic polynomial, the renormalization limit set, it lies on a flat interval on R, but now you took that renormalization limit set on the flat interval and you just wrapped it around the graph of your quadratic polynomial, right? This is how the degenerate map works. Okay, so then how does the direction transform? Well, everything is on this graph. So if you take a direction, which is tangent to this graph, then under the dynamics, it'll stay tangent to this graph. Okay, so the action on the direction field is trivial. So there's nothing to worry about. All you have to do in order to understand the geometry is the relative distances of points that are on this curve. Okay, but as soon as you turn on the Jacobian, as soon as you make it non-degenerate, you can see that, well, okay, so it's still perturbative. So the renormalization limit set will lie close to the graph of some 1D unimodal map, but the direction field starts to spiral out, right? So if you try to draw a smooth curve which stays tangent to all these direction field, it will be impossible, right? Yeah, so there's this kind of very bad transformation of directions that start to happen as soon as you become 2D. And this problem gets worse and worse as the map becomes more and more 2D, right? So as the Jacobian increases, you can see that what you see becomes more and more upsetting, yeah? So if you were to have rigidity, what that means is that, well, you not only have to map the points to points so that the relative distances are the same, but these directions also have to match up exactly between the two maps, right? So it's a more difficult problem. And it turns out to be not true in general. So in general, you don't have rigidity. So you won't have a matching of the way directions are transformed in the dynamics. So here's the final slide, and these are the results about rigidity. So let's take two maps, two Hénon-like maps, which is infinitely renormalizable. And let's say that you have this kind of topological correspondence between the two renormalization limit sets. Yeah? So it turns out that a parameter which is of fundamental importance is something called the average Jacobian. So basically, you take the Jacobian of the two maps, you average it out on the renormalization limit set. Yeah? If you're comfortable with Oscillatet's theorem, think of this as just the negative Lyapunov exponent of your map on this Cantor set. Okay? So then the first rigidity theorem came from the work of Lyubich, Martins, and Di. So they worked on just perturbative maps. So you're using the power of the 1D hyperbolicity. And they showed that, like I said, you don't have rigidity in general. Okay, so if the average Jacobians are not the same, then there is no smooth conjugacy between the renormalization sets. Okay, and Misha and Marco, they told me that at the time when they found this out, they were surprised by this lack of rigidity result. Because you have such nice convergence of renormalization, they thought that they should be able to recover everything that you have in 1D for 2D as well, right? And they were also surprised because numerical simulations at the time showed that there should be rigidity, but then there isn't. And actually, the reason for that is explained by their second result, which says that, yes, so you won't have a smooth map conjugacy everywhere, but you have it almost everywhere. Okay, so intuitively, you can think like the spirals that you see in the previous slide, it only becomes infinitely bad on a set of measures zero. Okay, so this is the result that they have, at least in the perturbative case. And when I first learned about this work, which is like more than 5 years ago now, I remember getting the sense that the outlook on the dynamics of Hénon maps was something kind of pessimistic. It almost felt like this kind of way that us one-dimensional dynamists like to do things, where we just take the dynamical system, you look at its phase space, and we try to understand everything that's happening in the phase space. this seems like a luxury, which is very unique to 1D situations. So if you, as soon as you go to higher dimension, you have to learn to be happy with something less information. You have to learn to be happy with, for example, just giving a statistical description of the dynamics, right? And you have to be able to ignore what's happening on sets of measure 0. Okay, that seemed to be the kind of outlook that we had in Hénon-like map as a result of these kind of results that Misha and Marco had. But fortunately for rigidity, we don't have to give up quite yet, because it turns out that the techniques that we developed with this quantitative Pesin theory and how it combines with the renormalization method, it turns out to be sufficient for controlling how this death spiral happens. Okay, and then we recover this kind of rigidity in the case that the average Jacobian stays the same. So this is in development, so it still needs to be written up. But I feel confident that I can prove this, yes. And then the last result that I'll mention is that actually if you go all the way to the other end of the spectrum, so that you have area conserving map, there's actually a result of these 3 authors, Gadishev, Johnson, and Martins, who says that there you have rigidity as well. All right, I think that's about it. So thank you so much.
Are there any questions or any comments? If not, perhaps we can thank Super again.